Welcome back. In this section of the lecture, we'll be dealing with this concept. We'll define what signal-to-noise ratio and how it depends on equivalent noise temperature. I'll define what noise factor and noise figure is, and then we'll find the cascade formulas for noise figures, and we will particularize we'll apply the concept that we know for equivalent noise temperature in attenuators, and we'll find we'll do it in terms of noise figure. Now, in our communication system, our receiver will have to process an input signal, and it will also pick up some noise from the antenna or whatever source our receiver is connected to. So both the signal and noise at the input will be translated at the output, right? Now, the total output noise it will be given by K T out B, being T out the noise temperature, the equivalent noise temperature at the output, which is the gain multiplied by the sum of the source temperature plus the equivalent noise temperature of our system, right? Now, in any communication system, or in most systems, we are required to fulfill a given signal-to-noise ratio, right? The signal-to-noise ratio is the ratio of signal power to noise power, right? And there's usually a specification which is called the SNR, which has to be satisfied. Now, the signal-to-noise ratio at the output can be calculated as the output to signal power to noise power, and you can do this, and from the equations that I've given, this ratio is equal to the ratio of input signal power to the noise power that represents the antenna or the source plus the equivalent noise temperature of our receiver, right? So this ratio in here will give you the signal-to-noise ratio at the output of our receiver, right? On the other hand, at the input of the receiver, we can calculate the signal-to-noise ratio, which would be the power of the signal divided by the noise of the signal. And here the power of the signal divided by the noise that comes from the antenna or the source. And this noise is K times the equivalent temperature from the source and the bandwidth. So we can work out how much is the degradation in the signal-noise ratio between the input and the output of the device. And if you do this, you will find that this degradation between input and output signal-to-noise ratio is 1 plus the equivalent temperature of our system divided by the equivalent noise temperature of the source, right? The antenna noise temperature or whatever this is, right? Note that this degradation depends only on the ratio of equivalent temperatures, right? It depends on the ratio of the equivalent temperature of our receiver to the ratio of the equivalent temperature of the antenna over whatever source that we have, right? Now, for this degradation in signal-noise ratio does not depend on the gain of the amplifier, it does not depend on the bandwidth, and on many other things, right? Now, for the particular case of Ts equal to T naught, this degradation of signal-noise figure is called this degradation in signal-noise ratio is called the noise factor, I'm sorry, right? So the noise factor will be the ratio of signal-noise input to signal-noise output, right, for a particular value of T sub S equal to 290 Kelvin, right? So this would be equal to 1 plus TE divided by T naught, right? So there's a one-to-one relationship between equivalent noise temperature and noise factor, right? They are related to this equation in which a T naught also plays a role. Now, This F, it's defined as the noise factor, and is defined in the standards for the International Telecommunication Union, as I showed in the earlier slide. Noise figure is defined as the noise factor in dBs, as 10 log of F. I have to say, however, that in many instances, people use F indistinctly, and they call it noise factor or noise figure, and they may quote it linearly or in dBs. So this distinction between noise figure and noise factor in many practical instances is not used. And that finishes this section of the lecture on fundamentals of noise.